So this is my online notes for microelectronics circuit analysis and design. And the book is by Donald Neamen. And so chapter 1 starts out with basically just talking about the silicon as a semiconductor. And first it talks about basically its intrinsic silicon and its extrinsic silicon. And so we start out by saying that we have silicon, which we can represent by its symbol Si, and it has an atomic number of 14 and a atomic mass or weight of 28. And this is a group on the periodic table. This is a group 4 element. And then what that means is that it has 4 valence electrons. And since its atomic number is 14, we know it has 14 electrons. And we could write it out: 1s2, 2s2, 2p6, 3s2, and 3p6. So that's 14, or 3p2. So that's 14 electrons if you count them up. And this is the 4 valence electrons. And it's important because the valence electrons are the ones that are involved in bonding and reactivity. And so first he shows that you can draw sort of an isolated silicon atom like this, and you can put it near some other isolated atoms and so forth. And if you made a bond between the silicon atoms, and I'll show the typical chemistry bond where a dash is represented a covalent bond, and each covalent bond is represented by 2 electrons. So I'll just put little dots out here to represent the other electrons that are not involved in the bonding. So this represents 2 electrons. And it's kind of annoying in the book is that he represents 2 electrons like this, where this is what a chemist would write as a double bond. So each one of his dashes represents 1 electron. But in chemistry, if you took general chemistry, that would represent, each dash would represent 2 electrons. So it's kind of confusing about that point. But I'll stick to the chemistry convention where 1 dash is 2 electrons and then a dot is an extra electron there. And basically shows, if you draw out a little box here, that when you have a sort of an extended crystal lattice, that the silicon is in a tetrahedral arrangement. So we'll draw just a little box here. And at the center of the box is you have a silicon atom. And then if you go down to the corners and draw another silicon atom and another silicon atom, and then another up here at this corner and another over here, whoops, at this corner, then you would have a tetrahedral arrangement of atoms where we could draw it like this too, using a wedge and dashes. And so each one of these is a silicon atom. So it's in a tetrahedral arrangement. That's all he's showing there in the book. let's see, new, don't save. Whoop. Okay, so on the next part of it, he basically says that at when the temperature is equal to 0 Kelvin, uh, the lattice is basically in a static state. It's not moving. Electrons can't flow at all. And he gives this diagram of basically your band energy. So down here at the bottom part, if we just say this axis is energy, down here, all your electrons that are in that covalent bonds, let's draw it again. And each dash represents 2 electrons again. All your electrons at t equals 0 down here in what's called the valence band. And they can't move around. They're just stuck there. Valence band. If they could move around, they'd be in the conduction band up here. Conduction. They'd be up here. And he calls this EV, and EC is that line basically for the conduction. So this is the maximum energy that exists in the valence band, and this is the minimum energy that exists in the conduction band. And the energy difference he calls EG, or the band gap energy, or we call this the forbidden band. Because nothing can exist in this forbidden area. It's either in the valence or it's in the conduction. There's no in between. So as you increase the energy, as you increase temperature, so as your temperature goes up, then the electrons get enough energy that they can, if they get enough energy, well, basically, if they get EG or more of energy, okay, if the electrons acquire EG or more of energy, then they can make the jump up and become a free-moving electron in the conduction band. And like I said, the electrons can't exist in this forbidden band area. And so this band gap energy, EG, how big this energy is for a particular material will dictate whether it is a conductor of a semiconductor or an insulator. Okay, so the band gap energy dictates that. And that's sort of an intrinsic property of the material that you're working with. And so if your band gap is greater than 3 but less than 6 electron volts, then we're talking about a semiconductor. And if your band gap energy is on the order of 1 electron volt, then we have whoops, I did that wrong. This is an insulator. This is an insulator if it's 3 to 6. And then if it's order of 1, then we have a semiconductor. And if it's much, much smaller, then it becomes a conductor. So basically this energy gap becomes smaller and smaller and smaller, then it becomes more of a conductor of electrons. And so if we look at table 1.3 in the book, silicon has a band gap energy of 1.1 electron volts. And then gallium arsenide has a band gap of 1.4 electron volts, and then pure germanium was a band gap of 0.66 electron volts. So these are all semiconductors. And when it gets enough energy to let's make a new page here, new page. When it gets enough energy to basically go into that conduction band, you could think of it as something like this. So we have these silicon, And well, let's draw this as a here's where we have a spot where the electron, where that covalent bond has been broken. And then we have the other atoms in the lattice here. And we could say that the electron that was there kind of moved over here somewhere. And so now we have this positive hole and this negative electron. So we call this a hole, H-O-L-E. And holes can flow around and electrons can flow around in your lattice, in your silicon lattice. So if we drew something like, where this is 2 electrons, just like you typically see in chemistry, 2 electrons, and then we could say, here's a spot where there's a hole, a plus, okay? And then we have another silicon here, and I'm not drawing out the rest of the lattice. And then this electron could move over here, and the hole could move over here. And so then we have a plus, and then an electron, and 2 electrons here. So now this hole is kind of float around, and the electron has. So holes and electrons, so this is important, holes and electrons both contribute to the flow of current, that you would see in the system. Now the concentration, or sometimes in the book he calls it density of these holes or electrons is given. So you could have the number of holes in cubic centimeters, or you could have the number of electrons in cubic centimeters. Okay, so that's your concentration of your carriers. So concentration or density of carriers, charge carriers, is given in number of holes per cubic centimeter or number of electrons per cubic centimeter. And in an intrinsic, and I mentioned this word before, intrinsic semiconductor, the number of holes is equal to the number of electrons. Okay, and an intrinsic semiconductor is basically a pure substance. There's been no doping of other atoms into the crystal lattice. Okay, and so all the holes or electrons have been generated as a pair due to thermal energy, as I've talked to before. So once you get enough energy, that covalent bond breaks and generates an electron and a hole together. And so the intrinsic number of carriers is equal to Ni, and it's given by this formula, Bt to the 3 divided by 2, e to the minus Eg over 2kT, where B, they don't really name it in the book at all, and they just say it's basically a constant depending on material. And for a silicon, it's equal to 5.23 times 10 to the 15 15th over centimeters to the 3, K to the 3 divided by 2. T is the temperature in Kelvin. E is that band gap energy again, where again I said for silicon it's equal to 1.1 electron volts. And then K is the Boltzmann constant. Boltz. I got into some weird mode here. And I have no idea how to get out of it. Oh, that was weird. How do I get back to my pencil? Okay, we're back in the pencil mode. That was weird. Okay, so the bolts, BLEZ man constant, and for us that is equal to 86 times 10 to the minus 6 electron volts per Kelvin. Okay, so we have everything that we need here to calculate out what the intrinsic number of carriers is for silicon. And so in example 1.1, the author asks you to calculate the Ni for silicon at temperature equals 300 Kelvin. And you just plug it into that formula. Say N equals, and the B we already said was 5.23 times 10 to the 15th. And then Kelvin is 300 times over to the 3 divided by 2 power. Then we have E equals minus 1.1 divided by 2 times your Boltzmann constant, which was 86 times 10 to the minus 6 times 300 Kelvin. And you just plug that into your calculator and you get 1.5 times 10 to the 10 number of carriers, we'll just say number, divided by centimeter to the 3. So this says that we have, for an intrinsic semiconductor, we have 1.5 times 10 to the 10 holes per cubic centimeter, or 1.5 times 10 to the 10 electrons per cubic centimeter. Either one, it's just a number because of intrinsic carriers, and they're both equal to each other. And if you go to like Wikipedia and you look up silicon, and it tells you that the density is equal to 2.3290 grams per cubic centimeter, okay? And also you can find that the atomic weight is equal to 28.085 grams per mole. And then from general chemistry, 1 mole is equal to 6.022 times 10 to the 23 items. We'll call it items. And items can be, atoms, electrons, photons, whatever. It doesn't matter. That's what 1 mole is. It's 6.02 times 10 to the 23 things. And from that, you can calculate the number of atoms per cubic centimeter, which is going to be 2.3290 grams per cubic centimeter times 1 mole is equal to 28.085 grams. And then then you have 6.022 times 10 and 23rd, and we're talking about atoms here, in 1 mole. And if you do the math, then you get 1, or no, you get 5 times 10 to the 22 atoms per cubic centimeter. And he gives this in the book, but he never derives it. So I was just curious how to calculate it, so I calculated it myself. And this is much, much greater than the 1.5 times 10 to the 10, say, holes per cubic centimeter. So your number of holes, or your number of electrons in an intrinsic semiconductor at 300 degrees is much, much less than the number of actually atoms that are actually in a cubic centimeter. So this concludes the first lecture, or notes.